So it's 9:30. I appreciate that people are still joining, but I was just going to start with the first talk, which is very much a word from our sponsors. So just to get that done and dusted before we get on the technical content. So I will just, and I do apologize if I'm slightly clunky with this, because it is only the first time I've given a course using using a Windows machine. So so hopefully people can see that. Okay, so this is just a general overview of the way ARCHER2 training works, and I'll go through it quite quickly. But so ARCHER2 is the new-ish UK National Supercomputer Service, managed by UK Research Councils and EPCC. It's housed, operated, and supported by us, EPCC, and hardware support. I've got Cray there. Apologies, it's HPE. I need to. The company's now HPE now. It's a Cray machine, but the hardware is an HPE machine. I should update that. Hopefully the logos have been updated correct. Yes, the logo is correct. The HPE Hewlett-Packard Enterprise. As part of that service, we provide training for the computational science and engineering team. That's 60 days per year, essentially at various locations. But of course, we went online during COVID, and people seem to like it. So we're keeping quite a lot of the training online anyway. ARCHER2 is located at EPCC's Advanced Computing Facility. It's about 10 kilometers south of Edinburgh. That's a mock-up. This is what it actually looks like. This on the left is the initial 4-cabinet system. I show that picture because it's got the back off, and you can 1, 2, 3, 4 cabinets. You can see all the wiring. But this is ARCHER2 in all its glory now, with a nice front piece on. We have a machine called Cirrus, which is a tier 2 machine. Just briefly, what's EPCC? Well, we're the closest thing the UK has to a national supercomputer centre. We've been around for over 30 years. Originally, we were called the Edinburgh Parallel Computing Centre, but we're technically now just EPCC. We're a self-funding centre at the University of Edinburgh, and we've been running national parallel services since 1994, and that coincidentally was also a Cray machine. We do a whole range of research and commercial projects, including postgraduate teaching and HPC training courses. And this is just to say that, if you came away from this course and wanted to collaborate, we do a lot of projects. But I mean, EPCC staff, in terms of research grants, appear just like research associates. So a lot of our staff work full or part-time collaboratively on other research grants. We used to do a lot of European projects, but of course that's shrinking for obvious reasons. You're not in Edinburgh. Here's a nice picture of Edinburgh. It doesn't show the two major things at the moment: overflowing with tourists because of the festival, and overflowing with rubbish because of the bin strike. But that's very much an artistic tourist picture. Here are the resources. You won't need these, I think, because hopefully the course is self-packaged, but there are other resources there, training for past courses as well. My name is David Henty. I'm in charge of education and training at EPCC, which is the MSc, our praise training centre, I'll mention later. And I don't run the ARCHER2 training program. That's run by my colleague Juan, but I give courses on the program. And my HPC research is in sort of parallel program models, accelerator performance. And performance includes IO, which is where this training course came from. Please fill in the feedback form at the end. General inquiries afterwards, go to the ARCHER2 help desk. I'm going to plug our MSc here. We've been running an MSc for over 20 years as part of the University of Edinburgh. And there's some graduates from a few years. Actually, quite a few of these people on this picture ended up working for us. It's a standard UK taught masters course. We also developed a supercomputing MOOC, massively open online course under the PRAISE project, which, I mean, I don't know if it's interesting to you guys. You probably know more than this, but it's a very conceptual introduction to supercomputing. No programming involved, but not trivial. It covers the concepts with thought exercises and such. Now, it's run in a self-study mode. The material is, we don't support it actively. We don't monitor the chat boards, but you can access it there through that URL. During the course, you get personal accounts. The course will be closed for up to about a month afterwards. The course accounts will be closed 2 weeks after that ends. So, but don't worry about the course material. So you have access for about a month or so afterwards if you want to carry on using the system, playing on with the exercises. But the materials and stuff are archived on the ARCHER2 web pages, so don't worry about the material disappearing. Longer term, there's lots of ways of applying, but if you want to just get some access to try ARCHER2, this gets you 800 compute units at 800 node hours for up to 12 months just by doing a little driving test, just showing that you've read the documentation and understand that you're not going to trouble the help desk too much once you get an account. The security in the room is not relevant for this course. And there's a code of conduct which we expect everyone to obey by, just the usual, be nice to each other, be constructive. We all have very different backgrounds. We're all expert in some things and novices in others. So you can look at that if you have any issues. There's also funding calls, regular calls, where we fund longer term software projects that are targeted at ARCHER2. So we might fund somebody for 6 months or a year to develop some software to scale up to the scale of ARCHER2 or something. The hardware software setup I won't cover because we'll cover that in the exercises. That's not particularly relevant here. We're also still part of PRACE, which is a big European project which runs till the end of the year, and this course also forms part of our PRACE training course. That's coming to an end with the end of PRACE. PRACE has a lot of members, 26. The UK is represented by us on behalf of the research councils. And there are 10 training centres. I think these will be carrying on in some way beyond the end of PRACE at the end of this year, but it's not clear at the moment. If you want to know about upcoming courses, there's a couple of URLs here. There's a central URL for PRACE, which shows you all the PRACE training courses. So I hope you enjoyed the course, and please ask questions. Chat is the best, although we can drop to audio. I will monitor the chat, and so please ask questions as you go along. So for those of you who maybe came a little late, that was just a message from our sponsors, so you didn't miss anything technical and particularly interesting. I just wanted to get that out of the way at the start. You may have seen I mentioned ARCHER2 quite a bit there. That's because this course is delivered under ARCHER2, machine under the service, and we will be using ARCHER2 as the platform for the exercises. But if you notice, the course doesn't have ARCHER2 in the title, and that's because this course is the material and the techniques and the code is very portable to other systems. The details of the performance and the setup will differ, but the course is largely relevant to any parallel machine that uses a parallel file system, and particularly if it uses the Lustre file system, and that is becoming pretty commonplace now, Lustre. So that's, I used to have ARCHER2 in the title, but I've taken that out because I hope this course will be useful to people who are not ARCHER2, even maybe not planning currently ARCHER2 users, just interested in parallel I/O as a general concept. So I will just so you should see the ARCHER2 page here in a second. There we go. And so under training, we have upcoming. Now, when this course finishes, it will be moved in a week or so into the course repositories, where we have material from all the previous courses, which will include the slides and the recordings. But at the moment, we're looking at upcoming training, efficient parallel I/O, and the course materials here. It points to a slightly scrappy GitHub page that I've put together, but it does have the timetable. So what I'm going to do is, before 11, I'll talk about the challenges of parallel I/O and Lustre as a file system in general, but also a bit about how it works on ARCHER2. And I may truncate that talk because I'm just very keen before the first break that we do a practical, mainly to check everyone can log in, and then if there are issues with login and any other such issues, we can fix them over the break. So if I'm running a bit late, I've reconfigured the course slightly since last time, so the timings might be awry by a few minutes. It's quite a relaxed timetable, hopefully with plenty of time for practicals. And yeah, that's why I've scheduled it like this. We'll talk about parallel as a concept, how Lustre works, how MPI-IO works, and I'll explain why I'm concentrating on that, although this isn't a course about MPI-IO. I'll talk about that. I'll talk about how the ways you can configure the Lustre file system, and then I'll talk about other I/O libraries. And then we'll finish at 3:30, but there is a session from 4 till, I say, 4:30 here, which is to finish the exercises, or generally for Q&A. I'm happy to answer any questions you might have. And these give you links to the parallel exercise sheet, which will download. That seems to download okay. That's fine. And also the IO benchmark, which will download later on. So I'm just about to give the first talk. I didn't know if there were any. You should be able to. You should be able to see a chat window now. I've just typed into any questions there. You may have to click on an option to open it up. But if there are no questions now, I'll just carry on and give the first lecture. Could somebody type something into the chat just to make me convinced that I've got my notifications set up correctly? I'm supposed to get an audio notification, which is very useful when I'm lecturing if someone asks the question halfway through. Great, it does work, thanks. Again, and I'm using this system for the first time for training and a different browser, but that's great. Thanks very much, that all worked. So I will now hopefully I get the right one here. Right, so what I'm going to talk about first is the challenges of parallel I/O. So, this is really, we're trying to solve a problem, but it's very important to say what that problem is, why I/O is difficult, why parallel I/O is difficult. Now, I have a model in my mind of what people want to do based on my own experiences. But I gave a seminar recently, and there were people there from the climate research community who actually used I/O in a very different way. So please, ask questions or make comments if you have questions which aren't covered by these slides. But I am trying to give just a very general overview of what the challenges are. So I'll cover why I/O is difficult, why parallel I/O is even worse, the kind of solutions that people do tend to use in parallel, but why they might give problems, and why we should really use the I/O libraries, which is what we're going to cover here. What are we trying to do, and then a bit about playing this down a bit, because I used to cover MPI-IO a lot more here, but I'll talk about the general concepts. Again, I'll often use MPI-IO as a model, but actually the MPI-IO uses the same, very much the same approach as the other higher level libraries. The higher level libraries might be easier to use, more convenient possibly, but the concepts are very much the same. And they almost, I'll cover this, they almost all use MPI-IO at the end of the day. So that's why MPI-IO is important. So why is I/O hard? Well, there's a whole bunch of reasons. It breaks out of the nice process memory model. You have a very virtual view when you run a program. You have a process as memory. You don't need to care how it's laid out. This data has to physically be on an external device. There's a disk somewhere, a physical disk, which the data has to appear on. And that can be very restrictive. I mean, a file is basically just has a linear access, just a little string of bytes. That means random access may be very inefficient because you have to seek, and on old systems which are actually spinning disks, a physical disk head had to move. You may have to reorder your data to write it out. If you ever looked at I/O, it becomes very system specific. A whole bunch of things here. I mean, you can use text. The number representation might be big or little endian. There's all these libraries, HDF, NetCDF5. Fortran has its own slightly strange undocumented formats and things. Then disk systems themselves are very complicated. I mean, I will use the term disk here, but actually what I call a disk maybe a bunch of disks, redundant array of disks, therefore both performance and redundancy. There's many layers of caching. You may think you're writing to disk, but you're not. You're writing to an intermediate disk. You might write into memory. So I think I/O is the HD equivalent of printing. You buy a nice new laptop, you bring it home, it all works, you connect to the internet, that's really easy. Then you try and connect up your printer, you try and get stuff from your laptop onto a physical external device, the printer, and it's just a nightmare. So that's sort of, it can be quite problematic and nasty. But the higher level libraries are there to hide its complexity. And this is going to be one of my standard examples I use to illustrate the problem. So I'll just illustrate what I'm doing here. So we've got, I'm just going to use we've got a double array of X of size 4 by 4. Now, that has 16 elements, okay? So, and they'll be numbered in some way. You can argue if it should go row-wise or column-wise. It doesn't really matter. So these elements, so an array of double x44 actually gives me an array of 16 pieces of memory. So I've numbered them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And you know, this will be row-wise or column-wise, depending on whether you're C or 4 channel, whatever, but it doesn't really matter for this example. And in serial, I could just write that out to a file with fwrite x, size of double, 4, I've got 16 elements, and this file pointer is something I previously opened to point to a file. Now, in parallel, so what happens is that data is written out in this order, 1 to 16 on disk. So it's already been linearized. In the program, we have it as a nice 2D array. We can talk about xij, but the file is just 16 elements. But what we're going to do, I'm imagining a parallel program where this 4x4 array is actually split across a grid, a 2x2 grid of processes. And so these data elements are owned by 4 different processes: a yellow process or processor, a blue one, a green one, and a red one. And although this is almost the most simple example you can imagine, a very small 2-dimensional array split evenly across a grid of 4 processes, you'll see that the I/O pattern on disk is already really rather complicated. So the data from this process, the blue process, is scattered into the file. So this is going to be the problem we have in parallel, that we have to rearrange the data to go into lots of different places in the file. So if we wanted to do this in parallel and end up with the same file on disk, which will turn out it's probably what we want, there's going to be quite a lot of work done in that the data from this red process has to be split into 2 sections here, and that first section goes there. Then we have to take a gap, and that one goes there. So it is already beginning to see what the difficulties are going to be. And in fact, the way that parallel file systems are constructed makes this even more challenging. Because not only is the data split across multiple processes, the file can be split across multiple disks. And we'll come back to that later. So in parallel I/O, okay, what we would actually have is each process would actually have a double array of size 2x2, because it's in parallel. I've numbered the processes 1, 2, 3, 4. And what we want is some magic parallel I/O call, and some magic goes on here to get the same layout in disk. The reason I've got local different numbering here is that really, okay, although process 2 owns elements 3, 4, 7, and 8 globally, in a parallel program, it really is a 2x2 array with elements 1, 2, 3, 4. So, I mean, we can argue whether it's, so I've used sort of local numbering here. So elements 1 and 2 of the process 4 data go here, elements 3 and 4 of the process 4 data go here. So this is just the question is, what is the magic parallel I/O call to achieve this with the least pain? So the naive solution is something like this, okay? In an MPI program, we would declare the array, we would open the file, every process would open the same file, okay? That's already an issue, but let's say we do that. And what you might say is, well, I'll get each process to seek, okay? Each process will basically seek to a particular place in the file and then write, okay? But you'll have to do this multiple times, because of course, process 4 would have to open the file, seek to this point here, then write its first 2 data elements, then skip and then write again. And that's why I've got ... here, okay? So already you can see this is kind of nasty and difficult, and you have to compute what these offsets are and such like. And also this will not work in general. Multiple processes writing the same file, problematic, okay? Unfortunately, Unix was invented back in the early 70s, 50 years ago, when nobody thought about parallelism. So, fundamentally, multiple processes writing the same file is problematic for lots of reasons. But even if this worked, okay, the performance will be very poor. It would require many, and this is a tiny example. Imagine a much bigger example. It would require many cycles, hundreds, thousands of cycles of seek, write, seek, write, seek, write. And if there's one thing you have to have in the back of your mind, disks are optimized for a small number of large writes. Disks are optimized to say, could you please write this 4 gigabytes of data? Not write the 16 bytes, skip a bit, write 60 bytes, skip a bit. That is going to kill your performance by orders of magnitude. So this will not work in general functionally because of the way that standard Linux file systems work anyway, but the performance will also be poor. So why is parallel I/O harder than serial I/O? Serial I/O is already a bit of a headache. We cannot have multiple processes writing to a single file. Unix generally cannot cope with this. This is because of the way the caching works. Okay, I'll have a diagram which illustrates that. But again, because I/O is slow, the way that memory access is slow on modern processors. So the way you make memory access faster is you don't access memory. When you write data, it goes to a cache. Okay, and then the hardware manages that. So you have so the same is true in disk file systems. Data is cached in units of disk blocks, which is typically about 4K. But unfortunately, because Unix wasn't designed to be parallel, these are not kept coherent. I'll illustrate what I mean by that on the next slide. You might think, well, surely I can have, so it's not even sufficient to have processes writing to distinct parts of the file. You might say, well, surely it's okay here if everyone opens the same file and writes to their own section. Well, in general, that's not going to work. Now, it might work if you have a parallel file system, but what a parallel file system will probably do, at least as a naive solution, is every time you access the file, it will lock the file. It will say, well, I'm a parallel file system. David might be writing for multiple processes. I better minimize client file. But that locking will serialize the I/O. So not only will you have each process doing a very complicated set of I/O calls, they will be happening in serial. Serial is the death of performance. Even reading can be difficult. You might say, isn't reading easy? Well, if you have 1024, or now, if every process on ARCHER2, which has got 750,000 processes opened a file, I cannot believe a file system could cope with 750,000 opened files at the same time. And as we said before, the data is distributed across different processes. So processes don't in general own contiguous function of the file. If we've seen that a process will probably want to write file to multiple locations. You can't do big linear writes, so the performance will be poor. And actually, we'll see in a parallel program, you often have junk data as well. Local data may have halos to be stripped off. The halo is you might have a boundary swapping code which has temporary halo data, and that may parallel I/O is a bit of a nightmare. And this is just to illustrate the point. The problem here, if I want to read, modify, write a file, I might have a file here on disk. I've got 2 processes. So the file, let's say the file is split across 3 disk blocks, okay? And these might be 12, 4K. This is just for example. Okay? Process 1 wants to read the first half of the file. So it reads the first half of the file. But what locally will happen on that process or on the operating system is it will say, well, I can't, my minimum quantum for a transaction is a disk block. So David wants to read the first a bit of the second. Well, I'll read the whole lot in, okay? That's fine. So you read the whole lot in here. And the same on process 2. So process 1 has disk block 1 and disk block 2 in its cache. So does process 2, okay? Fine. Then it actually goes into memory. And then you do some calculations. So process 1 alters that data, and process 2 alters that data. And then later on, you write the data. So it's written. Now, when you write data, it goes to the disk cache. Okay, that's a tip. This is why you should never pull a USB stick out of a computer, because when you write that USB stick, it might not be writing to the file. It might be caching it in memory. But sometime later, maybe the cache gets full, or your program ends. The operating system goes, okay, David's finished with this. I better actually write this to disk. He wants this really on the external disk. But each process assumes it's the only one which has accessed the file. So process 1 might flush the disk like that. Then process 2 flushes the disk, and you get garbage data, because at least standard Unix file system isn't built to cope with multiple simultaneous accesses. I said a parallel file system like Lustre may get the right answer, but it would do it through locking and such like, and it would just be very slow. So that's just to illustrate that things are quite complicated. So as I said, the first naive solution, which is everybody writes their own little part of the file, just isn't going to work for both functionality and performance. The second naive solution is independent I/O, also called file per process. Each process opens its own data file and writes its local data. Now, this is very simple to implement, okay? But I think it's a nightmare to cope with in practice. You know, this may have worked when I started in parallel computing back in the 90s, you know, 100 processes, 100 files. But, you know, if you're running on 1,000, 10,000, 100,000 processes, it's just going to be a nightmare, because you're going to end up when your program finishes with thousands of files, and this will require a lot of pre and post processing. The other problem there is the data format depends on the number of processes. What I mean is, if you run a program with 100 processes, you get 100 files. You run it on 200 processes, you get 200 files. So that you get a completely different output from the serial code. And maybe I'm being slightly pedantic here, but I find this philosophically wrong. Parallel computing is an optimization technique to make the program go faster, but you should get the same answer. And so I think that's true both for the calculation and the file. You know, I think that, you know, you should get the same output file, modulo, rounding errors and whatever, with a parallel program than a serial program. I think, you know, having a data format which is fundamentally dependent on the number of processes that you run your program on is just, if people have this method, we'll see later on that there is a way of having the best of both worlds. But, you know, if you just naively write, you know, process 0 dot that, process 1 dot that, process 2 dot that, I guarantee you will do a lot. You will end up with huge numbers of scripts for pre and post processing to try and reassemble the global data. Like, it just gets quite nasty. So what I mean here is that, you know, if you just do this, everyone opens a local file, which is maybe called data1 dot that, data2, data3 dot 4. If you do this, this actually may be fast. So that is its advantage. And in the benchmark program I distribute, this is one of the I/O modes. And for a number of reasons, you can get very, very fast I/O here. So that is its attraction, but its disadvantage is just the sheer number of files that you end up with, and the data handling aspects of that. However, we'll see Lustre is optimized to support this kind of I/O pattern to some extent. So this is what we want to achieve. I think that, as I said, that we have some parallel data. We want to achieve the same output as our serial program. We want to get this, as if we'd written this in serial, we want to get the data like this. So naive solution number 3 is controller I/O. You send all data to or from a single controller process. Now, this is clearly quite simple. MPI has those scatter gather routines which help that. And you write, so you just gather all the data into a single process and you write it out. So it's this main advantage is that the output is the same as the serial code. So you've achieved, my philosophical aim, which is to get the same answer in parallel as in serial. But there's two issues. First of all, you quickly run out of memory on the controller. ARCHER2 has, I should know this figure. It must have, I don't know how much data, but it has a lot of memory. Okay. What you're saying here is that I cannot write a file which is larger than will fit on a single process. So clearly, now then you can do it in small chunks. You can gather the data in from different people in different orders. So you can solve this by batching up the data. But we'll see the other problem is that the performance is poor. Because by definition, with controller I/O, we have a single process writing. And this is a serial solution, and there's no benefit from a parallel file system, or little benefit. Now, that may not be obvious at the moment, but we'll see later with a simple analogy, hopefully. The problem with this is that the performance is typically poor because you only have one process writing, and the I/O rate from a single process is limited by a number of factors. And we'll investigate those factors with our benchmark. So what do we need? We are to do parallel I/O properly. What I mean by properly, where the I/O system deals with all the system specifics. On a single file format, we already have on the serial format. We want the data to be in the right order. What I mean by that is stored according to their position in the global array, not dependent on where they happen to live on different processes. 1, 2, 3, 4, 5, 6, 16. And a number of libraries exist, and we will consider MPI-IO first. Now, I've hopefully illustrated in my abstract for this course. I am not going to go through how to write codes using MPI-IO. It would take more time than we have today, but you will see an example in the code. But the MPI-IO model is important for two reasons. A, it is a perfectly good model for parallel I/O, but it's effectively the same model that all the other libraries use, but also the other libraries will ultimately use MPI-IO. So if you understand the performance characteristics of MPI-IO, you have a good handle on the performance characteristics of the higher level libraries, because all of them build on MPI-IO at some level. So basically, if we're going to have an I/O library, what does the I/O system need to know about the data? Well, it needs to know how the local array should be stitched together to form the file. But actually, when you write an MPI program, the mapping from the local data to the global file is only in the mind of the programmer. Okay, the program, when you write an MPI program, you have multiple independent processes running, and the fact that they get together to solve a global problem is because you have made them communicate in the correct way. The program or the operating system doesn't know that we imagine the process to be arranged in a 2D grid. So what the crucial step in parallel I/O, okay, clearly you're going to open a file, write the data, and close the file, okay? But the crucial extra step in parallel I/O is we have to tell the I/O library what portions of the global file each process owns. Okay? That's the crucial additional step in parallel I/O that you don't have in serial I/O. You have to say, okay, I'm process 3, and I have 4 data items, but they should go in that location, that location, that location, and that location. That's the crucial step. Now, all the libraries have their own way of doing this. I said, so your programmer view, you may think of this, but the machine, this is actually an old picture of, I think, the HECTOR system from years ago, thinks it's just running 4 processes, each with arrays of size 4. Okay, this is your mind. That's not what the computer doesn't really know that. So you think of the file as a large array, and imagine we're recreating a single large array on a controller process. Now, the model, the I/O system wants to create this array and save it to disk, but it will do all the clever stuff. It will hopefully not do naive controller I/O. Okay, it will do a number of things. It will do a small number of large I/O operations, hopefully merging data to write large contiguous sections at a time. So hopefully, but by describing the entire I/O problem you want to do, it allows an I/O library to aggregate data in clever ways and do a small number of large writes, not a large number of small writes, and also use any parallel features. Okay, using multiple simultaneous. If there's multiple I/O nodes, we'll come back to this. Use them, and all the issues about any coherence issues between blocks will be dealt with. So this is why we should use I/O libraries. They are relatively straightforward to use, hopefully, but they hide all this complexity. So they're easier to use than doing it by hand, and it turns out typically more efficient. And the MPI-IO approach, MPI-IO is part of the MPI standard. Each process needs to describe what subsection of the global array it holds. That is the crucial extra step. And in MPI-IO, this is done using MPI data types. Now, I'm going to cover this. I'll have a lecture where I go through this conceptually. But the MPI-IO approach is each process uses. So basically, what you say is the green process has to say, I own this 2x2 subsection of this 4x4 array. If you remember, this 4x4 array doesn't really exist. I mean, that's your global data. You do that using MPI data types, and there are a number of data types you can use, but there are already data types in MPI to do this. They weren't designed for MPI-IO, but they've kind of been hijacked for MPI-IO. And there are a number of data types you could use, vectors, subarrays, and such like, if you're familiar with that. Other parallel I/O libraries exist. MPI is usually the lowest level, but you may never call it directly. The higher level libraries I'll talk about here are HDF5 and NetCDF. HDF5 is very commonly used. NetCDF I've come across in the climate weather modeling community, but HDF5 is much more dominant. More recent is ARCHER2. I'm afraid that ARCHER2 is not currently a part of my benchmark. I'd hoping to add it. But the approach is always the same. You have some method of describing what portions of the file each process owns. and these libraries, and then you do, and these libraries usually use MPI-IO to do their reads and writes at the lowest level. So summary, parallel I/O is difficult in theory and in practice. MPI-IO provides a high level of abstraction, and the crucial step of describing the layout of the data is done using derived data types. And MPI-IO hides all the system-specific details, but hopefully takes advantage of them for performance. We'll discuss the crucial issues later on. They're much more flexible and modern formats, NetCDF, HDF5 and NetCDF2, and I'll talk about these at a general level in a later lecture. They gain performance by layering on top of MPI-IO. If you want to use MPI-IO, you need to have a good understanding of derived data types, which is maybe something you might not have covered, but that's what they build upon. So that's the summary. So I've talked about the problems, the difficulties of MPI-IO. The next lecture will be talking about, just trying to find my correct. The next lecture will be talking about the Lustre file system on ARCHER2 in practice. But I always planned a 5-minute break here. I'll maybe if I just stop. So we are actually on time. Hopefully I didn't go through that too quickly. Where our next talk will be the Lustre file system. I say Lustre file system on ARCHER2, but I'm using ARCHER2 as an example. This is very much a description about how Lustre works. And if you use another computer, maybe another tier 2 service anywhere in the UK or elsewhere, it will probably be very excuse me, it'll be very similar. Does anyone have any questions? I'm going to take a 5-minute break now. I've got a glass of water, and you don't want to hear me. But are there any questions about that, or anything? Anything you'd like me to address, which I can do individually, maybe the one-to-one. We can do breakout sessions. Okay, so that's like, so if there aren't any questions, what I will do is I will basically okay, so hopefully you can hear me again. So I had a question that came in from Christian about parallel IO and a shared memory. So actually, if I'm thinking about OpenMP here, actually, maybe if I the problem you have in let's see if I can find my right. I think I've closed the window. This file, no, it's there. Okay. Yeah. The problem you have in it's taking a bit of a delay on this. Fine. The problem you have in parallel IO is that the process of reassembling this data from distributed processes into a single file requires physical communication between processes, between compute nodes. But if this were a shared memory program, I would expect that you would have this data in a shared array. And the fundamental difference between shared memory and distributed memory programs in OpenMP and MPI is that in OpenMP, any thread, if it's a shared array, can read any part of the data. So what you would do here is you could just you would just pick a. So here, controller I/O, i.e., doing all the I/O through a single thread, typically the controller thread 0, isn't a stupid thing to do, because the thread can just read all the data. But in terms of performance, I don't think a threaded program will benefit much from a parallel file system. Well, that's maybe not. It's interesting. It depends on the system. Typically, parallel file systems get their performance from having multiple nodes, which are multiple computers, right? Each computer has its own network connection. Each node has its own network connection. But by definition, a shared memory program runs on a single node. So I would naively say that the shared memory program doesn't benefit from a parallel file system, but the practicality of doing parallel I/O are very easy, because any thread can read all the data. However, I need to think about that in the context of ARCHER2, because that may not. Yeah, that's an interesting question. My naive answer would be, function is easy to implement because each thread can read all the data. But parallel I/O isn't such a big. Unfortunately, a threaded program won't benefit much from a parallel file system, as we'll see later, because parallel file system benefits from there being multiple nodes writing at once, and an OpenMP program only runs on a single node. But okay, well, I'll maybe think about that. That's a good, interesting question. So what we're going to talk about now is just there's a bit of a delay here. Okay, parallel file systems and Lustre. When I first started giving this kind of course, which was almost 20 years ago, kind of course, not these, there were lots of parallel file systems around. But actually, people seem to have converged on Lustre, which is quite good, because it means that we can make general comments about the hardware. So this is not a hardware course, but you do need to understand the way that parallel file systems are built to understand the performance characteristics and how to make the best use of them. So I'll cover parallel file systems in general, the Lustre file system, striping, which is the key concept in parallel I/O in Lustre. Other parallel file systems have similar concepts to striping. This is where you store a large file across multiple disks, but it's maybe not called striping. And some simple Lustre commands. I'll talk about what the bottlenecks are, and the purpose of running the benchmark is to try and investigate what the bottlenecks are. So the results you get will depend on your particular target system. But that's why I wrote the benchmark, was to try and understand how best to configure the file system, and how best to use the file system, how best to use MPI-IO and other libraries, but also to use it to investigate the various bottlenecks. So how do we build parallel computers? Well, it's often a surprise to people. We don't go out and buy very expensive processors. We buy standard processors, each not particularly fast. Typically, we actually run them at a lower clock speed than you would on your laptop because of energy and heat. But the performance of parallel computing comes from using many processors at once, an Archer up to 750,000. And that requires manual distribution of data and calculation across processors if you're writing your own program. By that, I mean, MPI calls, send and receive, broadcast, gather, scatter. It's up to you. And if you take a serial program and run it on a parallel computer, it ain't going to go any faster. You have to do something. You have to manually rewrite the program to distribute both the data and the calculation across processors. And people almost universally use MPI for that. Although on a single node, up to maybe a few hundred cores, you could use OpenMP. Parallel file systems are very similar. Construction of many standard disks, each not particularly fast, but the performance comes from reading and writing to many disks at once. And in MPI, we talk about processors, each one being an MPI process. Probably what is more important for the file system is it requires many clients to read and write data to different disks. And the way that Lustre works is each node. So remember, just ARCHER2 is a fairly standard system. It's built up of 6,000 nodes, each of which has 128 CPU cores. So you're typically running 120 MPI processors on each node. But what the file system sees is it sees 6,000 nodes as clients. Okay, so that's how the parallelism works from the calculation side. Each node, each compute node, of which there's 6,000, is a separate client of the file system, and so they can do their own I/O. But also data from a single file can be striped across many disks. So we can actually hopefully increase the bandwidth by having, and we'll talk about these details later on. However, this is clearly very complicated. If we're going to have data from a single file striped across many disks, or if we'll see serial files stored on different disks, we need to have some record. When I want to open a file, which disk is it on, which part of the file is on which disk. It has to appear as a single file system to the user. When you do ls-l, you don't want to see, well, your file stored on 57 disks. Here's the 57 files that it's made up of. You want to see a single file, and that means there has to be a controller, and that's called in Lustre speak called the metadata server, the MDS. So that can be an important issue. So this is a generic picture of what a file system looks like. We have application processes running on compute nodes. We have a lot of processes, P naught up to Pn-1, each with their own memory, where here n on Archer is 750,000. We have some high-speed network, which on Archer is the slingshot network. And then these processes can read and write to the Lustre file system. And the Lustre file system is made up of lots of, so there's various levels of virtualization here. I'll go through them here, but I'll hopefully point. So there's a metadata server for each file system, which knows where everything is stored. That's your catalog of files. But you physically have things called object storage servers, which are boxes. Okay, I'll show them the things you buy. The metadata server actually has some storage, so it's on some metadata target. So typically, this is often actually a solid state, like a solid state disk for performance, because this can become a bottleneck. But each object storage server has lots of object storage targets, which I will call disks. They're a bit more complicated than that. But it turns out that as a user, the two things you care about are the metadata server, because it can become a bottleneck if lots of people are trying to talk to it at once. And you don't really care about the fact about this intermediate layer. You care about these object storage targets, which are disks. So I will talk about metadata server as being the thing controlling the file system. And I will talk about I will sometimes say lots of disks, but technically they're called object storage targets. Okay? And you can have and how many of these you have and how they're mapped depends on your system. But I'll give you the details for ARCHER2 just so you can understand any results you get. So I don't have pictures for ARCHER2, but these are actually from Archer, but they're quite nice pictures, I think. Each OSS, this was object storage server. You could buy them. Okay, but it actually had multiple. I think this had 2 or maybe 8. I can't remember how many disks in it. And they're stuck. It looks quite nice, actually. The disk systems actually look more high-tech, more Star Trek-y than the actual compute system for some reason. But basically, your disk system will be some huge rack of multiple boxes, each of which has lots and lots and lots of disks in it. And we'll see what those numbers are for ARCHER2. So the terminology is Lustre has lots of different levels and virtualizations. Object storage server can have multiple object storage targets. And each OST, I will call this a disk because it's the smallest object you see as a user. And actually, each of these OSTs is fundamentally a separate Unix file system, a separate Linux file system. So fundamentally, when we do striping, your file is stored on multiple OSTs, and that will somewhere hidden deep down will be a file system with a small file, which is the fraction of the data on that OST. You don't see that, but that each OST is a separate Linux file system. But I will call it a disk for that reason, because have a quite naive view of these things. So when I talk about things, so each OST will have many physical disks in a RAID array for redundant. Typically, there's maybe 10 disks. So you have 8 bits and a parity and 2 parity bits, which allows you to recover from multiple bit errors and such like. But that's really a level we don't care about. I will talk about the metadata server, which is the database that contains the information on e.g. where a file is stored, and the object storage target, the physical device that stores your data, which I will typically call a disk, although it contains probably multiple hard drives. So the MDS and the OSTs are what a user interacts with, and that's what I will use. On ARCHER2, we have a compromise to make. If we have lots and lots and lots of OSTs, okay, in a file system, that gives us big bandwidth, but it means that the MDS, the metadata server, has to deal with a lot of disks and possibly a lot of clients. Okay, it might get overloaded by a number of clients. So if we have a fixed number of OSTs, we could put them into a single file system, okay, which would allow that file system to have massive bandwidth. The problem is then that this metadata server would have to deal with lots of OSTs, but also lots of users, lots of clients. And so what we do on ARCHER2 is we take a compromise. We have 36 OSTs, but we split them to 3 separate work file systems. And there are going to be 4, I think, because we're inheriting one from the intermediate system, but currently there's 3. And we will be on one of work 1, work 2, and work 3. I don't know which one we're on. We can find out. This is a compromise between performance and, but yeah, a compromise between bandwidth and basically latency. Each has 12 OSTs and 1 MDS. So that's an important point. On ARCHER2, your file system has 12 OSTs, 12 physical storage units, and there's a single metadata server. Each group, project, consortium is assigned to different partitions to share the load. And multiple file systems mean the MDS is less likely to be overloaded. There is a file system with solid state, not spinning disks, technically NVMe. It's still to be fully configured. I do have results on it, which I may have time to show. I don't think we have access to it at the moment as users. We expect better latency, e.g. for small I/O transactions, and it may also yield better bandwidth. So I believe the plan is to have this as kind of a burst buffer, somewhere where you can do very fast I/O during your job, but will later be transferred into the standard work file system. I don't quite know the details. Each work file system has around 3.3 petabyte of storage, a total of around 13.2 petabyte. Now, when I looked up these figures, I got confused because I couldn't work out how I worked out as 13.2 petabytes and the data said 14.5. That's because I'm not normally pedantic about these things, but 2 to the power of 10 is 1024. 2 to the power of 10 is not equal to 1000. Okay. So I'm not normally pedantic, but I do try and say use the correct terminology, which I think is petabytes, kibibytes. This is this means power of 2, and this means power of 10. Now, when you're down at the gigabytes, it makes precious little difference. Up at the petabytes, you can see it's actually a 10% difference between the two. So what happens by default? By default, on a parallel file system, and then Lustre in particular, if you create a file, each file is stored in a single OST. So the default striping is 1, or you can call it an unstriped file. And which OST it's assigned to is decided when the file is created. And what Lustre will do is it will distribute them across available OSTs to balance the load. And I said each OST is actually a separate file system. So if we have this setup here, and you use controller IO, where well, first of all, it means that if you create a file, it might end up there. But remember, these resources that ARCHER2 is going to be running lots of jobs at the same time. So you may create a file that goes there. Someone else creates a file that goes there. So when you read and write, you're using different hardware. So hopefully you don't contend with each other too much. So that's good. So that means that your isolated from other users. But also, if you create hundreds of files, Lustre will distribute them in some fashion across lots of OSTs. And so again, you're using the bandwidth of multiple disks at once. And so that's very important. So reading and writing multiple OSTs from multiple nodes can benefit from reading and writing multiple files from multiple nodes can benefit from multiple OSTs. But access to a single file will not benefit from the parallel nature of the file system, because a single file is stored in a single OST, and typically you're limited by the disk is typically the limiting factor. Disks are quite slow compared to memory access and networks and such like. So if you have a serial file striped, so if you have multiple files, you'll benefit from the parallel nature of the file system, because different files will be stored on different disks. But if you have a single file and you don't stripe it, it will sit on a single disk, and you won't benefit in general from the parallel nature of the file system. And so if we want to write a single file for ease of maintenance and data processing, but we want to get high bandwidth, we use striping. Parallel performance in Lustre comes from striping single files over multiple OSTs. So you have a single logical file, big file.dat, but when it's created, if it's striped here across 1, 2, 3, 4, 5, 6, 7 OSTs, the operating system, or here Lustre, divides the file into stripes if requested by the user. And these stripes are stored on different OSTs. So that's the way that Lustre gets good parallel I/O for a single file. If you ask it to stripe the file, it will stripe it, distribute it across many OSTs. So striping allows multiple I/O processes to access the same file, increases the bandwidth as you're accessing multiple OSTs. It's typically optimized for bandwidth, not latency. So reading and writing small amounts of data is very inefficient on a parallel file system. Okay, so that is because if I want to access 1 byte, I say, could you please read that byte? It has to go, oh, where is that byte? Oh, it's on this part of the file, and it has to read it from there. I mean, it's very complicated. So this is optimized for bandwidth, not latency. But this is called striping. Striping of a file is fixed when it's created. It won't change under the control of the user. The fundamental parameters are the number of stripes and the stripe size. And so, for example, if my file is created with a stripe count of 4, Lustre might assign 4 to 4 OSTs, OST1, OST2, OST3, OST4, for the sake of argument. And what it does is it takes the stripe size and it divides this file round robin in blocks of the stripe size. So the default stripe size is 1 megabyte. And so the first megabyte of the file is stored on OST1, the second on OST2, the third on OST3, the fourth on OST4, and then back to the fourth stripe is on OST1 again. The fifth stripe is on OST2. The reason for that is, okay, if you wanted to read, if it divided the file up linearly in 7 contiguous blocks, if I wanted to read the first 10th of the file, it would be sitting on a single OST, so I get no benefit. By striping it, means even if I read a subset of the file, and it's big enough, it will be distributed across multiple disks. That's why it uses this round robin approach, not a block decomposition, but kind of a cyclic decomposition. To set the stripe, I find it easiest to set. Well, you can LFS set stripe -C sets the striping on a file. -1 is full striping, so that is 12 on ARCHER2. But that's if you want striping, you typically want to do LFS set stripe -C -1, and the file system will automatically put it across all the OSTs. You can change the stripe size. In practice, 1 megabyte, at least on ARCHER2, seems pretty optimal. This does not alter striping for existing files. It only okay. I always set stripe on directories. So I typically do this in a directory, and that means that all the files in that directory will have the same striping. I find that easier to manage. So you'll see my benchmark has different. If you want to investigate the effects of striping on I/O bandwidth, I have three different directories which you can set to be different stripings, and that's how I do it. Parallel IO to stripe file, you can see it's complicated in practice. Where in the file does the local data need to be written? Which OSTs are the stripes located on? Are there write conflicts? We need to use a parallel IO library to hide all this complexity from us. So the default, it's one megabyte is the default, which might seem quite small, but I have not seen much benefit from changing that in practice. But you can play around with it if you want. Where are the bottlenecks? Well, I like analogies, and so here's a train analogy. Okay, it's not the world's best diagram, but we've got a long train, okay, that's pulled up into a platform, and actually there are 4 carriages on the platform. There's actually more. I haven't illustrated very well on the diagram. I should do this, but there are actually, the idea is there's actually more carriages off the end here. Okay, so it's a very long train. Okay, but it's a very, very long train, but we only have 4 exit doors from the platform. Okay, so there's a very long train drawn up here with 4 exits. This isn't the world's best diagram, I appreciate. And what happens is all the trains open their doors, and everyone runs, and they have to get out of the doors. So the idea here is each carriage is an IO node. It has data it wants to get rid of. Okay, each carriage is the IO node, of which there are 6,000 on ARCHER2, and each of these doors is an OST, of which there are only 12 on ARCHER2, and then the platform is like the interconnect where people mingle. So I should redraw this, but the idea is there are a lot more carriages off to the right here. So if I do controller OR, if I have a serial exit door, okay, that is like having no striping, okay. And you can see here the bottleneck is, you can get data rapidly, people rapidly reach the platform, data rapidly gets on the network, but clearly you can see very quickly, if you have a single exit door, a single OST, this is going to become the bottleneck. People are just going to have to queue up to get onto this, out of this door. So this is where the bottleneck will be for an unstriped file, using this analogy that we have a serial, we have one exit door. If we only have a serial train door, okay, this is controller IO, okay, then but we store the file on lots of disks. This is likely to be the exit. This is likely to be the bottleneck. This is why I'm saying that striping a file across multiple disks doesn't really benefit you if you have controller IO, because everyone has to run through the train to get to this one door. This is the bottleneck. Okay? The bottleneck of a single process writing, the bottleneck of a single door is the bandwidth out of here is much less than the bandwidth out of here. The other thing we might want to do is to do reduced train doors. Okay. The problem with this here is that we have 2 doors per carriage. Okay. That means we have 8 people. That may just cause congestion on the platform. We may just have too many people at once, on the platform. So it might be more efficient to match the rate at which people come out of the trains with the rate at which they exit the doors. And so if the bandwidth of our door is similar to the bandwidth of our exit door, so again, you can see that might be beneficial. And it relates to the number of processes writing per node. Okay, this diagram, has multiple processes writing per node, multiple exit doors per carriage. But this diagram says actually that causes too much congestion on the platform. We'll throttle the IO from each node so that we don't get congestion, and so that we're matching the bandwidth from the door to the exit door to the exit door from the platform. So my view of a parallel Lustre file system is very much this. I think of a train, which are the carriages, and these are the nodes. You have potentially multiple processes writing per node. These are these exit doors, but the platform has a limited number of, sorry, these are the train doors. The platform has a limited number of exit doors, which are what you're trying to get out to. So the obvious question, does the MDF become overloaded for large numbers of files? What's the maximum performance of a single OST? Can one process saturate an OST? Okay, Is it sensible doing this? Or is this going to be limited by that? Do we maybe need to have multiple train doors open? Can a node saturate an OST? Or is the network the limiting factor? How well do different IO libraries work with Lustre? What are the best stripe count and size settings? So what I did is I wrote a simple benchmark to help investigate this. It's called MPI-IO, and it writes a large 3D distributed array of double precision numbers. It's exactly the same layout as I illustrated in my first lecture, except it's not a 2D array on a 2D grid of processes. It's a 3D array on a 3D grid of processes. Now, it came from some work I did many years ago for a user who had a large 3D cellular automaton model, and they wanted their I/O to be improved. So I wrote a library for them, and which I turned into a benchmark. It's written in Fortran for those historical reasons. So apologies if you're not a Fortran programmer, but hopefully it's at least the concept will be legible. I mean, all these libraries are very symmetric between C and Fortran. There's not really any difference. You just may find the syntax of Fortran a bit. So this is where it came from. So summary, a Lustre file system has multiple OSTs. I think of these in multiple disks. By default on ARCHER2, each file is stored on a single OST. You need to check that because, I mean, on ARCHER, our previous system, we started off with a default stripe count of 4, but that turned out to be suboptimal. It meant that all files were striped. And as I said, most files are actually serial files, program files, little data files. You don't want to stripe them. But now the default stripe count is 1. Increased performance for multiple files, a single user writing many files, or multiple users each writing to a single file. So parallel file systems do benefit from even with serial files, but to improve the performance for a single file requires striping, and that's under the control of the user. And we hope that the parallel IO libraries see this and basically, you know, oh, the file is striped. David striped the file, so I will have multiple exit doors to match the multiple stripes here. So, you know, the configuration of, you know, whether it looks like that or like that with something which we expect the parallel IO library to decide on, and we can discuss what it does later on. But I do think this train analogy is relatively useful. So what I wanted to do now is to go on to the exercise. This 15 minutes, are there any questions? Are there any questions? These 15 minutes are really to take a look at the exercise, but to be honest, I think the main thing is for you to log into ARCHER2. So that would be the main thing to do, and check you can log in. Hopefully you'll have accounts, so you can give information on how to get on account. But I will bring up the exercise sheet first. I'll show you. So this is where my multiple window skills fail me. So so hopefully the idea is that this exercise spans the coffee break from 11, but to get you, so you know, you'll have time now to look at this and you know, and run it. But I think, you know, I think the initial exercise would be useful. You need to clone the repository and do some and create it. But I would, if everyone can get logged on before the 11 o'clock break, that's great, and then we can come back after the break and actually run this and look at its performance. So what I will also do is, now there is an enormous amount of documentation on the again, I have now. Okay, fine. If I, but you might want to read the IO benchmark works, what it does. There's a bit of documentation there, and it has a very basic set of command line options, which I have. They're very unsophisticated, which I apologize for. But basically, it can do serial IO from one controller process, multiple serial IO, file per process. It can do file per node. That's restricting the number of doors open on the file per process has 128 doors open on each carriage. File per node only has one door open, and it also does MPI-IO, HDF5 and NetCDF to a single file. So you can, but those are the two things to be looking at: the exercise sheet and the documentation, which is on the benchmark web page. But please make sure you can log in. We can screen share to resolve common problems. We have some colleagues here who can help you out with that. I will, for the sake of it, share the exercise sheet, because that's probably the thing which you're most interested in. Oh, it's disappeared. Okay, that's stupid of me. Oh no, it hasn't. There it is. So please, I'll mute now, but please, I'm around. I'm going to do some final checks that there aren't. I haven't been able to test the reservation in anger. So we do have a reserved set of nodes today for the course, and by default we will be using the scripts are set up to use those nodes, hopefully, and that's the thing I need to check. If I've messed that up, I will need to fix it. So I have 3 directories. Actually, can I just? I'm in the wrong window. So I have striped, unstriped, striped, and full striped. So unstriped is unstriped. Full striped is set the maximum value. But it's interesting to, you know, if you get a certain I/O performance on 1 stripe and a certain I/O performance on 12 stripes, the question is, you know, well, was 12 stripes optimal? So the striped is there to allow you to try some intermediate value, which I think here maybe, I mean, you can pick what you want, but I thought two or 4 maybe actually. But does that make sense? It's just, you can try, you know, no striping, full stripe on Archer, but it's a game. It allows you to test effectively scalability against number of stripes to get some feeling for that. Yeah, because sometimes 12 stripes can be too. Or you worried that maybe 12 stripes is too many. You know, maybe that's just overkill. So I would encourage you to. Oh, I've lost my window again. My brain can't cope. I would encourage you to look at the instructions on the GitHub page, because, as I said, the way the command line options work is not brilliant. Okay, it's okay, but it's not brilliant. So yeah, but hopefully you'll explain. So there will be, you know, you will see instructions in the instruction sheet to use this command to run the benchmark, but what it actually does. So by default, the benchmark does everything, all the stripings, all the 6 different modes, but you can select which of those you do. So if you specify one, it only does that one. It's not particularly brilliant, but it's the best I could do in the time available. Yeah, thanks for confirming. Yeah. Oh, that was maybe Alexei. Yeah, thanks, Alexei. Yeah, I managed to run it as well. Thanks. Yeah, so that did work. Yeah. So yeah, Alexei's confirmed that the reservation worked for me, but it's really good. Alexei's checked that I haven't hard coded anything in, which is specific to me. So I said the way it works, just to keep us sane, is I now have in a couple of minutes we'll have a coffee break. So please, it'd be good if people could try and log in, just so. So that PDF is. I'll go back. Maybe missed that. It's linked. It's linked in from the. Where is it? I'm just having real problems with these multiple windows, but
someone has helpfully shared it.
Oh, okay, sorry. Yeah, sorry. I'm just I have too many windows up here, and kind of an there we go. Okay, fine. I understand where I am. There it is. Yeah, so but it's linked in. It's linked in from the at the bottom here. So I would go to this page, which is the web page for the course materials page, which has the timetable, and then also has the parallel exercise sheet and a link to the thing. So I'll leave this up because it's also got the timetable. Oh, whoa, okay. It has the timetable, and I've not changed the date. It's not Tuesday, 11th of January today, is it? That's okay. But I will fix that. So hopefully now if we go to course materials, I have fixed that. Yes, there we go. We've fixed that there. So just to let people get a break, we'll restart in said here 30 minutes at 11:30 BST, just to let you all have a break, play around, maybe get familiar with the exercise sheet. Okay. And if you have any questions, type them in. I'll see them when I get back. I'm just going to take a little break now. Okay, hi everyone. So I thought I would wrap up this session by just with the practical by just going through some sort of results. So first of all, I'll show the yeah. So I'll come back to that, Joe. I'll just basically the idea here is that basically you can try and estimate the bandwidth of a single OST, which is the single door here by just flooding it, and that means writing lots and lots of files from lots and lots of nodes. Okay, so that's basically, you know, opening lots. So that's lots of files per process and lots of nodes. So that's basically just saturate an unstriped file, and that's a way of trying to estimate the limit, the bandwidth of a single OST. To estimate the bandwidth of a single process, we just basically, I would use an unstriped file, but you could use, but you can do it to an unstriped or a striped file. But my guess is it doesn't make a lot of difference. And basically, you just do it serial I/O here. That's basically a single process running from a single node. So it gathers all the data, which is very quick because it's over the network. So you don't see that and then write. So that's a useful figure to know. You know, what's the bandwidth of a single process writing? What's the bandwidth of a single OST? And then the final one is basically if you do this and flood the whole file system, you know, well, we can sorry, apologies. Yes, yeah, you can do. You're not able to do that at the moment because basically, if we open lots of files, we'll end up on lots of different OSTs. But we can basically try and do this and flood the file system, and we would expect the maximum bandwidth we get would be 12 times the bandwidth of an OST. So I sort of played around with those examples, and I came up with some ballpark figures, which I'm not sure, but they're ballpark correct. Sorry, and I got the wrong. So you know, we can actually run here on up to 32 nodes. There's 32 nodes in the reservation. Be careful not to hog it, but there are 32 nodes, which is 32 times, which is 4,000 processes. But basically, if I do the serial I/O, I get about 1.2 gigabytes per second. I don't know if that tallies with what other people got, but basically, I got 1.2 gigabytes. So that says a single process can write at 1.2 gigabytes per second, which is pretty slow. Did anyone have a figure for that? Yeah. Has anyone tried it to a striped file? Just, you know, so. Don't know if that helps. That's basically saying, you know, if we open up one door here, yeah, my guess is it doesn't matter if you have striping with lots of exit doors, because basically you're limited by that. I don't know if anyone tried that. I think that was one of the exercises. Apologies, just to check. Yeah, I don't know if anyone's had a try with the stripes. I can maybe I'll maybe submit that myself just to see if we could find that. Just check that out. I'm just going to run one in the background, and then we can. Okay, fine, Alexi. Thanks. Okay, so again, so these I/O speeds are always going to vary because there's only 12 OSTs and there's hundreds of users. So but okay, so that's what we expect. So again, you know, parallel file systems aren't magic. Yeah, doing serial I/O to a striped file is like running a serial program on a parallel computer. You don't really get any benefit. Okay, so that's useful. That's thanks. That's what I'd expect. My other apologies, I keep going off the end. I shall from current slide. Multiple processes with 128 per node. This is just trying to. This is basically completely saturating the to try to flood the file system, and you know, so I sort of maxed out about 100 gigabytes per second. You know, it seems to cap. So my guess was that a single node was about well, actually keeps going up. It's quite hard, but you know, I guessed a single node was about 15 gigabytes per second maximum. I actually did another test where yeah, I guessed about a single node was about that. It's that's quite hard. So basically, this is the bandwidth. This is basically the network bandwidth out of a node. Basically, you're saying, look, you know, if I basically sorry, this is scaling the number of nodes. I mean, so you know, it was sort of yeah. I guess. Well, actually, no. Apologies, I'm being an idiot here. If I do that, I get 15 gigabytes per second. So a single node is about 15 gigabytes per second. Okay, so that's quite clear here. A single process is 1.2 gigabytes per second. If I do 128 per node, I don't get 150 gigabytes per second. I get about 15. So that's clearly saturating the node, and it's not saturating the OSTs. You can see that I can get more bandwidth here. So I would say a single is about 50 gigabytes per second. A single OST is a bit harder to quantify. But if you assume this tends to level off, if it levels off at about 100 gigabytes per second, and there's some cap, I mean, around 10 gigabytes per second, I think, for a single OST, it's actually quite hard to estimate with this benchmark. I did another benchmark, which I only thought about later, where actually there is a the cleaner way to do it. So what I'm trying to do is to basically estimate the maximum bandwidth of an OST by completely flooding the entire file system, which is a very not a very nice thing to do when there's other users on the system. And then seeing what I get. And you know, there's 12 OSTs and getting about 100 gigabytes per second. That you know, that means it's in the order of 10 gigabytes per second. In fact, yeah. So the important point is that a single process can't saturate an OST on the node. That's really the most important point about these figures. That basically the total file system has a bandwidth of around about 120 gigabytes, 100 gigabytes per second. That kind of bandwidth. The other reason why these figures are quite hard to quantify sometimes is that there can be caching. So you think you're writing to disk, but it's been cached somewhere higher up the chain in some memory, either on the operating system or on the disk controllers. I don't know. But those figures are just about ballpark correct. This single OST is the hardest one to estimate from these figures. This 1.2 and these 15 are very clear. I was actually able to do this in a separate way, which is a bit a weird one, but basically you can tell Lustre not only not to stripe the file, but also to put all the files on a single OST, so all the files in a directory on the same OST. So basically that's what I did. I basically did this, which you can't do with the naive setup which I've got here. But whoops, I managed to do this here. I had lots and lots of people writing lots and lots of little files, but only to one OST, and that takes a special Lustre command where you say, look, I want all my files on this OST, which is a very unpopular thing to do because it will kill anyone else using that OST. But this figure these figures are ballpark correct, and they give you, so single process is about 1.2 gigabytes per second. A single node, that's like the network bandwidth, about 15, and a single OST is somewhere between the two. So you can see immediately no, they're not. To get the processors to write the same OST, you have to do something special. And I've not given you that command because it's kind of a bit antisocial. But you actually tell Lustre not only not to stripe the files, but also which OST to put them on. So you pick a random OST and say, could you put them all on that OST? So I didn't give you that command because it's a bit antisocial to do that because but I mean, you can get an estimate from this benchmark of around about yeah. So I'm estimating this 10 from this, and actually this does tally. Craig gave a hardware limit of about 11 or 12 for this, so that was sort of useful. Okay. So hopefully that was useful, but giving you these ballpark figures. But the main thing here is you can see that the I/O, we have a total bandwidth of around of hundreds, over 100 gigabytes per second across all the OSTs. So that's a nice figure to know. But a single process can achieve 1% of that, okay? And a single node can only achieve about 10% of that. So we're clearly going to have multiple nodes and multiple processes writing if we're going to get bandwidth. And if we want to get a single file, we can only do that by, if we want a single shared file, we can only do that by using an I/O library and striping. So the next talk will just go through MPI-IO, but hopefully I'll also try and illustrate how these concepts, the way that MPI-IO does it, apply to other I/O libraries. Apologies, I've run out of water, so I will literally 1 minute while I get some water, and then I'll start the next talk. I'll just get the slide up, and then I will go and get a glass of water. No, that's the wrong one. So apologies. Thank you. So I'm set up now, and I will just get a glass of water and be back. So this course used to be a bit longer and concentrate a lot on MPI-IO. I realized it was a bit too detailed, but so I've left one of the MPI-IO lectures in to go through how MPI-IO works, but hopefully use it as a way of also illustrating how how parallel I/O libraries work in general. So I'll cover the MPI-IO model, the basic file handling routines, setting the file view, which is this crucial stage of you telling the I/O library which part of the file each process owns. MPI calls out the file view, and achieving performance, which is the kind of generic part, which we can investigate using the practical example. I just want to double check what my timetable is. Okay, fine, that's right. So the I/O performance is quite yeah, we have the I/O, the practical is split into two, so it's fine. So comparing MPI-IO and the controller I/O, controller I/O uses a single process for read and write. This requires a buffer to hold the entire file on the controller, and that's not scalable due to memory limits. The MPI-IO model, each process describes what subsections the file owns, which it does using standard MPI data types. You pass these into the MPI-IO routines, and that's called setting the file view. And when you do the read and write, the data is automatically read and transferred directly. This is talking about reading here, actually, not writing. Sorry, but here it's saying data is automatically read and transferred directly to local memory, or data is automatically written from memory directly to the disk. So there's no single large buffer and no explicit controller process. Okay, so this is all handled by the library. Okay, there may be, we'll see, there may be controllers, multiple controllers under the hood, but the model is symmetric. The model is a completely symmetric model where everyone writes and the data magically appears in the correct place. So there's 4 stages to MPI-IO. There's opening the file, reading or writing the data and closing the file, which is like, par for the course for obviously any IO library. But the middle one is setting the file view. Okay, so all the complexity is hidden in setting the file view. This is, that's the key stage. This is where the derived data types appear. So this is I appreciate the confusion here. In practice, write is more important than read. Now I say that because rule of thumb, applications write about 10 times as much data as they read. Some applications read in a tiny amount of data, a configuration file, then write out some enormous amount of data. But if you're doing a weather forecast, you read in today's weather, you run a forecast, and you dump the weather every day for a fortnight. You've written 14 times as much data as you read. I say here the exercise to concentrate on read. That's not true. That's the exercises for the original course where I got you to write MPI-IO. So apologies, this slide is very slightly out of date. For you, the exercise concentrates on write. And you might ask, why do I do? Now, my bench IO doesn't bench read, it only benchmarks write. The 2 reasons for that are A, right, as I said, writing is normally more important than reading. Actually, if you can do the read, you can do the write. They're very similar. But also, reading is particularly susceptible to caching. It's quite different. If you read a file once, it will probably be cached somewhere locally, and then you read it again, you get an anomalously high IO rate. So actually, although IO rates are variable with writing, with reading they can be really hard to interpret. So that's why bench IO only does writing. So to open a file, it's collective across a communicator. You do MPI file open. You pass in a communicator, so that could be com world, but you can subdivide it. You pass in a file name, it's kind of obvious. You pass in an access mode, which is whether you create the file, maybe you do read only, write only, read write, standard stuff. You pass in an info object, which is used to pass in extra information I'll come back to, but you get back a file handle, and this is effectively the file pointer. This is very simple. Open a file across a communicator with a file name, with the various information on the access mode, and you get back. This is an info. I won't talk about that much because you can use this info object to say things like, first of all, the info is system specific. So if you're on a Lustre file system, you would use one set of info objects. If you were on a Spectrum scale IBM file system, you'd another set. So that's a bit awkward. But secondly, if we're on Lustre and I want to change the striping or the stripe size or the stripe count, I can actually do that by specifying something in the info, but I find it easier to leave the MPI calls simple, leave these unspecified, i.e. there's false, but change them on the command line. So I have not used the info much in this in practice. So attach the file to the file handle. It's like a C file pointer or Fortran unit number. That's collected, and the access mode is specified by A mode. So it's useful to specify the correct access mode. If you're only going to read or if you're only going to write a file, it's useful to say that. If you're only going to read it, it's useful to say that. May allow the system to do a bit more optimization. So examples in C. Actually, now so I'm going to do a quick poll because I just realized I wanted to know something. So apologies for this delay. You can't preset up polls. So hopefully you can see that. Do people write parallel code in C, C++, Fortran, Python, or some other? So I'll show the responses. Hopefully people can people see that now? I never quite understand. Can you see the results? Yeah. So it's interesting what the other was. I wasn't going to put it in, but to be interested to know what the other language was. I don't know who said other. Actually, I can find out who said other. It's a bit naughty. Yeah, I can see who said other, but it's fine. I just language. I'm just interested in what the other language was. But if it's fine, okay, I'll finalize that. So in terms of C, I've got a C example. Okay, Java. Okay, fine. That will be tough, I think. But in terms of C, there's a C example here. C++, C++, MPI, you just call C. Fortran is there. Python, the MPI for Pi interface gives you access to all of MPI from Python, including MPI-IO, but it's very much optimized for NumPy arrays, for regular arrays, and it can cope with general objects, general Python data structures, but the performance is atrocious. So, you know, so if you're going to use MPI for Pi, I've started playing around with it. It's surprisingly good, but you have to use NumPy arrays. Anyway, so we have an MPI file handle. The access mode, I call it MPI mode read only. MPI file open, MPI conwell, data in access mode. I'm not specifying any info, and I get a file handle back. Fortran's the same, except I have the error code at the end. And you can combine these access modes together with or addition in Fortran. So close a file. Hey ho, it's not very interesting. MPI file, close MPI file handle. There you go. It's collected across the communicator. That's fine. So remember, MPI-IO is designed to allow multiple processes to access the same file. So therefore, obviously, the open and close routines have to be collective across all the processes wishing to access that file. The other thing that you might be interested in is that, well, you'll notice that this, I mean, sometimes we say that any MPI routine that does communication takes a communicator as an argument, but that's not here in the close, but that's because the file handle remembers what the communicator was. So when you open the file, you specify the communicator, and that's squirreled away in the file handle. So when you call the MPI file close, the communicator is inferred from the file handle. There you go. So reading data looks deceptively simple, okay? You just, now I specify, here I'm talking about collective read, so everybody is reading. You can do individual reads, MPI file read, where only a single process reads, but we'll come back to that, or writes. These are all read, but the examples I have in the benchmark are obviously write, but the syntax is almost identical. A read is just like a receive. This just looks like an MPI receive, except you're receiving from the file instead of another process. And an MPI write looks just like a write, except you're writing to the file. You've got a buffer account and an MPI data type, and you get back a state. So it's a readable model, actually. An MPI-IO, reading data is like receiving from a file instead of receiving from a process. Writing data is like it's like sending data to a file instead of a process. So it counts objects of data type from the file on each process. This is collective across the communicator associated with file handle. It's similar in operation to CF read or Fortran read. Okay. However, you'll see that this call is the same on every process. Okay. You know, every process in my example, the MPI file read or file handle buffer for MPI int. If you think about my original example of a 4x4 array. Clearly, we're missing some information here because we don't want them to all read the same integer. We want them to read their section. There's no offset specified here, but process do not all read the same data. Well, there's this additional step I've missed, which is the crucial one, which is this setting the view. So in between opening the file and reading or writing data, you need to set the file view, and that is the crucial step. So It's called MPI file set view. It's quite a complicated routine in the, if I'm teaching this as an MPI course, teaching you how to use MPI-IO, I would spend quite a lot of time on this. But I just want to give the basic idea here. You're setting, so each process is saying, I want to read or write to this portion of the file. You specify the file. You can specify an offset, which is in bytes. It's a special type MPI offset. That's because this can be bigger than bigger than 32 bits. It's just a new type. The E type is what the file is made of. Is the file made of integers, characters, double precision numbers? The important thing is the data type. The data type, which you pass in, which we call the file type. The file type is the standard MPI data, and this is the critical bit where you specify. This is the part which the file type will differ typically on each process to allow each process to specify that it's interested in a different region of the file. The data representation I'll come back to, and again you can pass an info object, but again in practice I've not tended to use that info object. I've not used it much in practice. So this specifies the starting point in the file in bytes, which is a bit nasty bytes, but there you go. E type specifies the elementary data type, which is the building file of the block, which is building block of the file, which would typically be, well, for us, double precision. File type specifies which subsect of the global file each process accesses. That's the critical one. Data rep specifies the form of the data in the file. We'll talk about that later. Info contains hints and system-specific information. I'll not go into that in any detail here. But other libraries will have their equivalent of setting the file viewer. They'll call it something different, and I'll give some examples later on. But this is the crucial step in all parallel I/O. So the file view. So there will be a default view, but I think the default view is if you don't set the view and you do a file read all, everybody will just read the same data starting from the start of the file. So it's not compulsory because there will be a default view, but the default view is typically not useful. So does that make sense? I think that's a good. Someone has asked before, what's the default? I've never actually done MPI-IO without calling a set view, but I did play around once, and it seemed to have a default view, which everybody just starts at the start of the file. But that's not any use, and reads linearly, which isn't of any use. Does that make sense? So you need to call set view. Yeah. The default view is not useful. So for example, actually, that's a good question. Do I have the picture here? Yeah, this here. Okay, fine. So we want the yellow process to read 1, 2, 5, and 6. This guy to read 3, 4. If I didn't set the view and I did an MPI file read, they would all read 1, 2, 3, 4. That's what I think happens. Yeah. So the default view is it starts at the origin and you just read them from the start, which isn't what you want. Now, what you need is a data type which has gaps in it. And MPI allows you to do this. There's two data. I mean, the important point is that a 2D subsection of a 2D array, whether you're in CN4 channel, row, column, major order, is got gaps in it. So MPI already has data types which allow you to send non-contiguous data with a single send or receive, and they're either called vectors or subarrays. A slight technical difference which I won't dwell on, but what you want to do here is you want to make sure that, for example, that the rank 1 will specify a file type, which is this. So once rank 1 has specified that its file type is this, it's like a mask, and it sees none of it. So the rank 1 view of the file after the MPI file set view is this. It just sees 3, 4, 7, and 8. So if I say read 4 integers from the file, it will just read 3, 4, 7, and 8. If I say write 4 integers, it will just. That's why the write is so trivial. You say write this many integers or this many doubles, but where they go has been previously specified by this file type. So you can do linear reads or writes. The holes in the data type are skipped over. So it's like a mask. You just see that. That's the model. You mask out all the file except the bit you're interested in. So the file type should tile the file. So rank 0 needs to have a file type that looks like that. Rank 1 looks like that. rank 2 like that, and rank 3 like that. So if we do that correctly, we will then basically tile the whole file in the correct order that we want to. So you need to get this correct, obviously, for it to work. But so the question is, in MPI, how do you define a file type that looks like that? Okay. Well, so as then, if I don't know if people have used, I'll do a quick poll. How much detail I goes into depends on kind of what people's MPI knowledge is. So I meant to say MPI data types there, sorry. Just be interested if people are okay, so there's about a 50-50 split. Now, quite a few people have, but quite a few people aren't. So I will go through this quite quickly. But the important point about this data type here is it has two aspects. It has a leading gap to skip 1 and 2, and then it has block, gap, block. So MPI has a data type called a vector, which is a pattern of block, gap, block, gap, block, gap, but it doesn't have this leading gap on it. So that means if you want to use vectors to specify this distribution, everyone defines the same vector, which is block, gap, but they specify different offsets when they open the file. So they place that same pattern there, 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 or there. And that is done by different processes computing a different offset when they do the file view. So they're using the same file type, but they're placing it at different places in the vector by using a different offset. That turns out to be rather awkward, because computing the offset is, what's the offset of this? Well, it depends on the sizes of the file and your position. It's a byte offset, so it's a little bit horrible. It turns out MPI type subarray is more elegant, because MPI type subarray is like a vector, but it has two advantages. One is it generalizes to more vectors are specific to these 2D distributions. MPI type subarray generalizes to 3D, which is what I do in my example. And also, you don't have to compute it automatically puts in the leading gap. So there you go. So data representation is a string can be native intellectual. The fastest native raw bytes are written to exactly as in memory. There is a portable one called external 32. So there is this problem that although most people use Intel chips nowadays, native binary bytes can be big endian or little endian, you don't know. I always use native because when we want to do fast I/O, I would recommend native. And then if ever you went to a system where you had a different data representation, you would just read it in once and write it out again to convert. Now that's where things like HDF5 and NetCDF and ARCHER2 are much better. This will I should have said this. MPI-IO files have no metadata associated with them. They're just raw data, which is one of their major problems. Whereas more higher level libraries like ARCHER2, HDF5, NetCDF have a lot of metadata. So this would all be stored in the file. You wouldn't have to worry about this. So I'm basically saying here slightly that basically you can use vectors and different displacements, but it's nicer to use, this is saying you can use, I call them fixed data types, but this is using the MPI type subarray. This is slightly technical for this talk, so I should maybe have deleted these slides. So collective I/O is absolutely and utterly essential to MPI to performance. So for example, if I am a naive MPI user and I want to add together an integer from all the processes, I might send them all to a controller process who adds up the answers and then sends them back using send and receive. Okay, everybody sends to the controller, then they receive. That is an utter disaster. Yeah, because on 1,000 processes, you're sending 1,000 messages in and 1,000 out. On 10, you're sending on P process, you're sending 2 times P messages. Okay, so that is why MPI has collective routines for things like MPI reduce, MPI or reduce to do the summations. It will use a tree-based or some algorithm where the time scales is the logarithm of the number of processes, not linearly, and that will give you benefits of order hundreds or thousands. I mean, it's not just a bit faster to do a collective rather than do it stupidly yourself. It is hundreds or thousands of times faster. The same is true of I/O. If you don't use collective I/O, then your performance will be terrible. Okay, and the reason is that if you do write all, then the I/O library knows that everybody is writing. So what it can say is, okay, right, I know the I/O library at this point knows everything. It knows exactly how the data is laid out between different processes. So what it can do is it can say, okay, I know everybody is calling this routine. And so the yellow process has this data, the blue process has this data, but if I actually combine that data in memory before writing to file, I can do a single write of all this data, a nice contiguous write with no gaps, rather than write. So basically, it's called aggregation. The collective routines can aggregate reads and writes for better performance. And by better, in my experience, is hundreds or thousands of times different. It's not so much that collective I/O is very fast, it's that individual I/O is cripplingly slow. Because to do this individually, okay, the I/O library would say, well, I want to write this data. I don't know if everyone else is writing or not. So all I can do is lock the file, open it up, write that data, skip, write that data, and then unlock the file and close it, and then process these serially. So, you know, the collective I/O, which in MPI-IO means calling an underscore all routine, MPI file read all or write all, and in other libraries there will be a similar switch to do that. It will be done in a different way, but you have to use collective I/O. Collective I/O is crucial to performance because it's the only way the I/O library can do any optimizations and avoid serializing everything and doing everything in a horrifically slow way. So this is, you know, the two questions you get all the time. One is, I've introduced MPI-IO into my program. The I/O doesn't go any faster. That's because you need to stripe the file. Unless you're storing the file on multiple disks, it's not going to go any faster than serial. Or I've introduced MPI-IO into my file and the performance is terrible. It's 100 times slower. That's because you're doing individual I/O rather than collective I/O. And both of those generalize to all I/O libraries. The info objects I won't talk about because I said it's easier to tune the Lustre file system from the command line than to use MPI-IO hints. So I would always set the info to null. So summary is that MPI-IO calls are deceptively simple. You know, open, read, write, close, but all the difficulty, all the complexity is hidden in setting the file view. The user must define appropriate file types so the file view is correct on each process. And use collective calls whenever you can enables the I/O library to merge reads and writes and into a smaller number of larger I/O operations from or to disk. So I was just briefly going to share. I've been in the wrong window. Taking a while. Okay, fine. So if I actually go to the bench IO, you'll see that we have my blurb here, but we can look at the code. So for example, the driver routine is very simple. Well, not particularly well written maybe, but at some point, if you're doing just going through this very briefly. I'm looking for the right. Yeah, there's a. If it's case 4, which is the 4th example, we call MPI-IO write of the file name, the IO data, what size it is, and the IO. So this is basically, this is my, and I'm going to show you what this call looks like. IO.com here is, find this right. MPI, sorry, IO write. So let's find that routine, and that's in MPI-IO.F90. And what it does, I mean, it basically, so actually I should also, I'm sorry, this is my own code, but I haven't looked at it for so long that it's baffling me. I've also arranged the processes in a 3D grid by creating a, sorry, where is it? Here we are. Create a Cartesian topology, and I pass that through the back door, actually, which is maybe not the right thing to do. But okay, so for the MPI-IO, basically the basic stages are that the other slight subtlety to this benchmark is that the arrays have halos on them. So I wanted to do something realistic, which was a 3D, still simple, but a 3D grid made up of 3D subgrids. But each locally, because it was a halo swapping code, I wanted to have halo data. So the array sizes are n1 plus 2 by n2 plus 2 by n3 plus 2, but the actual real data is only n1, n2, n3. So the IO routines have to do two things. They have to A, strip off the halo data, and B, write the data to the correct type in the file. So I basically I create a file type here, okay, which is basically telling MPI what subgrid of the main grid I answer. It's a very simple way. You just say it's a 3D grid. This is the global size of the grid. This is the local size, and this is my starting position. So the ndim, the array G size, which is the global size, and your sub size are the same for every process, but it's the array start, which depends on your coordinates. So where you start from depends on where you are in the process grid. You also have to tell MPI whether this is a Fortran or a C program, because it needs to cope with the big endian, little endian and thing. Having done that, I just do file open, file set view, file write all, file close. Okay, so it's really quite, and it would look similar in C. It would look very similar in C. And yeah, that's really basically it. So this, if I look at the timetable, basically on time, we were going to do we're going to run this practical on MPI-IO performance just before lunch. We're just about on time, a bit early actually, and that after lunch I'll talk about how to configure the Lustre file system, and we can go back to rerunning that to try and see if we can improve the performance by configuring Lustre. And then a quick break, and then I'll talk about higher level parallel IO libraries, and I may actually, oh no, it's not a break, right, fine. Then a break, and then finally, you know, you can leave then if you want, or carry on the exercises. There are options in the exercises to also, you know, you don't have to use MPI-IO, you can use NetCDF or HDF5 if you're interested in those libraries. HDF5 is probably the one you're most interested in, I guess, from experience. You could look at that and see what the relative speeds of these libraries are. So that's all I had. I will put up the exercise sheet. I do find this file chooser difficult for no apparent reason. So, you know, for parallel IO, we expect the bandwidth to scale with the number of stripes. That's what we're hoping, because we've got multiple, as long as we've got multiple nodes reading, as long as we've got multiple nodes writing, we would expect to get linear scaling with the number of stripes, the number of OSTs. So basically, you can try this and then try with more nodes. You can actually go up to 32 here. I capped to 8 previously, but you have up to 32 nodes if you want to do something larger. So that will see, you know, does the, you know, are we scaling with the number of nodes? How do things look? We expect using non-collective IO will be very slow. Edit the MPI-5 replace with MPI-5. Right? This actually is so cripplingly slow you may not be able to see it. So maybe only try it on a few processes. You can try varying the data format. There was an inexplicable bug in the library previously where the external 32 didn't work in some cases. So that might be, but the main thing here is to look at the scaling of MPI-IO with to the different stripes. So this is going to write to all 3 directories, striped, unstriped, and full striped, and see how the bandwidth scales with different numbers of nodes across different numbers of stripes. And I would be good to go, for various reasons, it would be good to go to more than 8 nodes. 16 would be good. It's actually interesting to have more nodes than stripes. That's an interesting configuration. So yeah, I'll be around till 1, and then we'll reconvene afterwards after the lunch break. I will